So welcome to the first New York City local meetup of the Learning of Graphs conference. I think we are a group of people excited about very similar topics, but also with very diverse interests in terms of applications for, let's say, underlying mathematics and all these things. I think, the law conference, you all know about it. It has happened, I think, 2 or 3 times, I believe, so far. Or how many times? The conference itself. But this is the first, twice, right? So that's correct. But this is the first NYC meetup, and there have been several other meetups in various big cities. I hope this is going to be an event that will be occurring again in the future, hopefully sometimes here as well. Just like a short word about the host, right? So it is hosted up, by NJ, in particular the computer science department that I happen to be a member of. In case you do not know it, some of you know it already, that NZID is in the top 50 public universities in the United States and very active research. I should say that we're always looking for great faculty. So for those of you who are in the position to be looking for jobs, consider us. For everyone in the room, you already know that, but for those that are online, you do not know that, we are in a very impressive location in Jersey City with great views of the city and New Jersey. So I'd like to say many thanks to the student organizers. I've been helping very good with all of what we're going to see here. The people responsible for producing this, I'm just going to mention the names: Ali Parviz, Yankee Yu, Jacqueline Marsh, Yang Bagwang, Ying Chang Wang, and Derek Lin. I'm sorry for mispronouncing some of your names, it always happens. I'm just going to introduce the first speaker, who will be Anton Tsitsulin. Biography: Anton is a research scientist at Google Research in New York City. His research interests are scalable, principled methods for analyzing graph data in an unsupervised manner. He received his Ph.D. from the University of Bonn in 2021. So thank you, everyone. Go ahead.
Thank you, Yanis. And yeah, it's hard to underemphasize how impressive the location is. So I'm very excited as well to talk about graphs in New York, in New Jersey, actually. So the title of my talk is Large-Scale Unsupervised Graph Learning. And I'm particularly excited about the unsupervised aspect of learning with graphs. So that's what I'm going to talk about. I'll start with a quick overview of what Google Research NYC is and its work. And then I'll try to speak about unsupervised learning in theory and practice. So interesting theoretical development that we've been doing, and some interesting practical stuff that I think is interesting for graduate students around here. Then I'll talk about how we use modern machine learning accelerators for graph machine learning, and then I'll a short blog for library for graph machine learning, graph networks in TensorFlow. So I figured this is the first. I'm the first speaker, so I have to do this just once. Graphs, in case you don't know, are representations of relationships between some entities. And they have a very different number of edges. There are different node types, and they depict very complex structures of very different things, not just addition networks. And there are 2 types of graphs that we love and care about. One is far more prevalent in academia, natural graphs, when the relationship comes from some source of truth, some external source. So, for instance, thinking about payments, social networks, citation graphs, cohort graphs. One thing that our group is interested in a lot is similarity graphs. Similarity graphs are graphs where you have edges that are built from some underlying data, similarity or distance function. In that case, we start with, let's say, some collection of embeddings, then we try to find edges across data points. And it's good to reflect why we're doing graphs at all. Traditional machine learning or large language models. First, they allow us to do computations, complex computations on abstract data and different kinds of data. So we have a graph machine learning model we can apply to very, very different sort of stuff. And we can do computation and merge diverse data types. So if we have different node types and edge types, we can kind of like merge different encoders and like merge different information together. That allows us to handle multiple data, which is working in industrial applications. And like just to kind of emphasize this even more, graphs can be very, very complex. Like we have porous sites here implemented in academia that are citation networks between people and papers, but like in real work, we can model very complex systems. So for instance, this imaginary video sharing platform, has some kind of advertisements going on music videos, and then people can watch, can like, people can sell advertisements, they can be like skipped, or there can be like very, very many different relationships between these objects, so very different sizes, modalities, of each node and each set. And graph neural network team is a part of a broader graph mining group and research. We'll have our VP coming here tomorrow to talk, I think, about broader picture stuff. We are often dealing with billions of nodes and trillions of edges. And this is considered large-scale data. So we can do research on combining algorithmic ideas with kind of like machine learning systems and models. And it powers kind of basically every like Google product in some shape or form, including like search, ads, YouTube, and so on. And there we have some public information available, blog posts linked here. And just in case, I'll be sharing the slides, like links will be if you're interested. And the graph neural network team is kind of like, the idea is to make it easy to use this like complex structured data within networks, and then we do like research. We develop a library to express this focus. I'll plug this in later. We do like some infrastructure work, and then we kind of do custom models for this. So the fun part begins: unsupervised learning in theory and practice. And I want to start with kind of a notion of combinatorial optimization first. I think combinatorial optimization is one of the interesting things that we can do. Many unsupervised problems, we can solve many unsupervised problems in combinatorial optimization with graph neural networks. I use like a super broad definition that you probably won't agree with. Like it includes like clustering, assignment, selection problems, and many more. And there are like many different applications that are interesting. For instance, in active learning, like cleaning data, like even scalable clustering with site information. And then one common theme about these problems is that they're very hard to solve. You can like prove almost any of those to be like hard, and then like you like go and try to solve something simpler, or you can try to attack these problems with kind of like magical hammer that we all got in the past couple of years, and try to apply neural networks in particular to solve those. One example of a hard combinatorial optimization problem is representative selection. It's a very, like if we solve this, that would be amazing. That's a graph problem of basically like selecting data points for the machine learning algorithm to optimize its downstream accuracy. It sounds too good to be true, and the solution is like harder than hard under the hypothesis. And yeah, it's like super impossible to solve, very hard. The fun part is that we can try to attempt to solve it with graph neural networks. And the idea is very simple. We try to learn embeddings and representative jointness or representative selection. Let me just explain the problem a bit more. We try to select examples, right? So we want to select a diverse set of representative examples that would kind of like span the space of our problem, and yeah, maximize our classification accuracy. So we try to apply a very simple algorithm, try to optimize the coverage and the learning of representations. Learning is done by contrastive laws. The coverage is like modification of k-means, and yeah, like some tricks to avoid trivial solutions. this is the illustrative example of how this works. You know, we have a graph that has some attributes depicted here in color. We pass it through a GNN, and then we have some latent space, and then we select the representative that is closer to the median across it. And one, you know, then we select for training. One interesting part about this work, I think, is that if we don't have a graph, you know, we actually can create a graph, contrary to like many intuitions. Building a graph actually helps with this particular problem, verified in many different benchmarks against many different baselines. If we just create a similarity graph and do the same thing as I showed in the previous slide, we can actually like achieve a lift in performance that is kind of you know, unexpected for some people. So we, you know, lift the accuracy by like significant margin compared to non-end-to-end baselines. And yeah, the second finding is that constructing graph actually helps. This is kind of exciting for many different problems because, you know, we can build graphs and play our graph tools to actually like improve on the accuracy of our systems. There are many different baselines. There are like all like most of them are developed by theoreticians, so they have a bunch of nice modular algorithms that they analyzed with this particular problem without any particular success and coming to the good solution. And then we tried all of them to see that they don't really work as well. And we have this lift. And yeah, we set up these two column groups, and then this last one is just like clustering with GNNs. And that's what I'm going to talk next, because we have a method for GNN clustering for clustering graphs with graph neural networks, which I think is also exciting because it provides a nice view in graph pool, because, you know, like clustering is kind of a fundamental graph building block. That's one building block that we all love, that allows us to solve very large graph problems. It is just a nice formulation. It is solvable. We have many different losses and so on and so forth. And you know, pooling is just a weird thing that people do. But pooling of graphs is actually like super close to clustering, which allows us to build many great intuitions about this problem. In particular, I love spectral clustering because it's like such a nice bridge between some really hard conventional optimization problem and something quite easy to solve with linear programs in scalable fashion. And other nice thing about linear programs is that you can solve them with gradient descent. So that's what we're going to do. This is a definition of modularity. This is probably what you have in your like CS to 4D in you know, any graph mining class, classic clustering objective that has this linear formulation. And this is kind of a, if you notice, this linear formulation is kind of a sum of sparse and low rank matrices, matrix. So we can have like, we can pose it as a generalized eigen problem and solve this in an efficient manner. And well, you know, like we have a hammer, we have a speculative like this linear problem. Let's try to hammer down the problem and, you know, optimize exactly the same loss. And then, since this is a spectral problem and we expect the solution to be orthogonal, we can just use this as a differentiable orthogonality constraint on our embeddings. The great thing is that it doesn't work, you know, because if it did work, then it wouldn't be a paper accepted anywhere. This is not accepted GMLR, so happy. It doesn't work because it's slightly too restrictive of a formulation, and the embedding gets stuck, and only this part gets optimized. And this is not what we want to optimize. We want to optimize the actual objective of the, you know, of the clustering. So we kind of like make a much simpler, more relaxed regularization that just tries to preserve the cluster sizes to be kind of balanced. And this now works. Gradient descent magic. We optimize modularity, and this collapse regularization thing is just like allows the problem to converge to the solution that we want. there are some tricky tricks. So yeah, this clustering thing is kind of like has a very sharp minima for each particular good solution. So we have to kind of like perturb it. So we have to use very high dropout rates. Right now, what I showed is kind of like has matrix A in it for optimization. So we cannot just do mini batch too easily. Slightly sensitive to dropout rates and produces like kind of a soft clustering, but we get the threshold and still get decent results. Yeah, we'll not scare you with tables anymore. This is like a baseline quality feature. This is the baseline quality graph. Then merge them together. Beautiful things emerge, and we can leverage the information that is present both, and like use kind of cross correlation to improve the results by like some 40% or something. On average, across data sets, we have like a lot more experiments in the paper because we underwent a couple of revisions. What I want to talk about is not real data. If real data is boring, I want to talk to you about synthetic data actually, because that's one of the focuses we have in a group that we discovered with this particular paper that we actually love to do synthetic evaluations. And we for this particular experiment, we generated a bunch of stochastic block model graphs. And a nice thing about them is that we can vary different things about them. So for instance, scenario 1 is varying the strength of the signal in the graph. Scenario 2 is varying signal of the features. 3, 4, 5 are like about 3 and 4 is like the variance. Scenario 5 is like the slope of the power law. The average degree, and scenario 6 is like the slope of the power. So we can vary all these different things and like very precisely test about what our method is sensitive to, which, when it works, we can make beautiful charts compared to all of other methods. When it doesn't work, it allows us to debug the method and figure out when it doesn't work, what prohibits it from converging well, which is a really great tool because, machine learning is really hard to debug. Graph machine learning, even worse. Like I look at the graph, I look at the gradients, I cannot really tell anything about this. When I have a bunch of small synthetic graphs where I can control some properties, I can actually understand what's going on. For instance, like one of the previous versions of the method, I was just regression constraints, right? So it didn't work when I had like super high degrees in the graph. Okay, let me just try something else that we control for this. So that's how I came out with this particular thing. So we were so excited about this that we actually wrote a separate paper in KDD about benchmarking on synthetic graphs, and we benchmarked a bunch of things. And the main point of the paper is rant about how all classical benchmarks are in kind of a very specific subspace, which has very strong signal in the graph and in the features. But this is not what we actually observe in many production machine learning systems. Sometimes people give us very poor graph structure. Maybe there is not much information there. Sometimes people give us absolutely garbage features, and our graph machine learning tools should be working with that. And we want kind of models that can actually handle all the regions in the data. So we made this. There are many more beautiful illustrations in the paper, and we can study this kind of response curves to different properties, which I think is very exciting. So usually, like most of the time, unsupervised learning, including when you do it on graphs, is done through contrastive learning. So just to give you some idea about how this works, we have a graph, and we try to make some permuted version of the graph. In this particular case, I just pretend I shuffle the features. We can contrast these examples and then like use one of the contrastive or symmetric learning process on that. But the problem is that I live in the industrial world, and when I have an unsupervised machine learning problem, I actually don't have labels to pick to. In academia, it was very nice. I was developing an unsupervised learning method. I was looking at the validation set of my labels, and I was optimizing things. But now, on my job, I cannot actually do this anymore. But I still need to perform model selection. We have to optimize hyperparameters. I need to understand if I'm giving, like Google Ads, like an actual working model or not. before they slap me for not doing that. I need to debug things. So how do I do that? Without it's just very unsupervised, actually, with no labels. For that, we have to rely on kind of like weak signals. So that's a paper from last year that explores the idea about getting the signal, whether the embeddings are good or not, from the data itself, from the embeddings themselves. So the idea is that if we have absolutely random embeddings, these are probably not good embeddings. If we have absolutely, identical embeddings, which are also not good embeddings. So we want something in the middle between this two horrible things. And we propose like a couple of different metrics. One based on intrinsic dimension, another two based on like kind of condition number, which means that if we fit a linear regression to these embeddings, how stable it is numerically, coherence is something related to like theoretical analysis of linear regression. Self-clustering is just like about how well clustered points are in high-dimensional space. We can probably do more things, but I think it's really important to actually think about unsupervised problems in unsupervised ways. Then again, since I work in industry, I can call unsupervised problems that are actually supervised. The distinction is actually kind of weird. People have been calling self-supervised learning, unsupervised since probably word2vec is the first offender. When it tries to predict the next word, things are kind of you have a supervised laws, but then you have this kind of signal that is just generated from the data, which I think is still, kind of qualifies as unsupervised because we can still get loads and loads of signal from kind of free without labeling or doing anything human. And for that, one example that we released in the public is this like kind of large scale graph regression problem to improve general processing units. These are kind of the TPUs made by Google that solve, that are like large scale machine learning accelerators. I'll talk about them later. So we released this huge data set of very large graphs. So there is like kind of like more of a million graphs, and they have like many nodes. Contrary to the chemical graphs that people study, these are usually quite tiny. And it's like not a classification, but a regression problem, which neural networks absolutely hate to solve. So I think that's kind of make it a very interesting benchmark that is not occupied by anything. And then we ran a 50K Kaggle contest to have people, like radio student beat us by a couple of tenths of percent, which was kind of that was the point of it. It's still kind of interesting. And yeah, you have a paper in the data to the public. So let me just explain, because I think it's a very good problem. When you write something in your favorite machine learning framework, it gets compiled to some intermediate representation, and then this intermediate representation is translated to, let's say, like assembly for these beautiful chips. And I will focus on the central part. Central part gets the competition graph and then translates it into like translates it to the actual code using some heuristics. So for instance, when you have like you write something dense, it has like a matrix inside of weights, right? But how is this matrix actually represented on device? Like whether it's row major or column major order, it makes a big difference in performance. But it's actually decided by the compiler. So like you have all this kind of like tiny flags that influence the performance of the overall program that you absolutely don't control, which is great because we can optimize them with machine learning, and in particular with graph machine learning to make our accelerator service even faster. And yeah, I'll talk about this kind of like accelerators and how we use them, because I think that's also cool, and it's kind of like a unique thing that we have on Google. Yeah, so before all this graph neural network jazz, we had graph embeddings that were popularized with Brian, who will be speaking like in a couple of hours. The embeddings kind of like are meant to capture the properties of the original graph, and it's just great to give them to people that do machine learning, because like people these days, they only deal with embeddings. They absolutely can't deal with graph, sparse. If you do graph neural networks in your pipeline, it just becomes a graph neural network pipeline, because that's the majority of complexity. It's just dealing with all the different sized graphs, like unusual shapes, stacking, and so on and so forth. So, we come from a graph to an embedding. We love graphs. We have many algorithms available for them at very large scales. But the problem is that it's hard to integrate into the machine learning pipelines. So we transform them into embeddings. Each node gets its own point in low-dimensional vector space, and then we can use these distances to do like mean prediction, classification, everything we know about in graph mining. You can do with graph in the embedding space. A standard embedding algorithm, George et al. 2014, people learns to predict context in random walks. So if you have a random walks, it tries to predict the green node from the blue nodes. And then it can be represented in two distinct steps. First, you need to create a corpora of random walks, and then you train a skip-gram model that is in one-to-one work techniques. Oh, thankfully, Brian is not in the books. Like in a slightly transformed fashion, there's a formula for you. We have a path, whether path exists, we try to score one. So if the embeddings need to be close, if there is no path, embeddings need to be far away from each other across the whole corpus, and we try to optimize that. And there are a bunch of different machine learning pipeline architectures. You probably don't think about this a lot, but we can do different styles of prediction algorithms. In particular, this default algorithm is suitable for the batch processing. So, in order to scale it to Google scale, we need to figure out how to do scalable random walk sampling, and then how to do scalable training of embeddings based on this random walks, right? The problems with that is that first, sampling a graph cannot fit in a single machine. Oftentimes, we have a couple of billion nodes, couple of billion edges, then it becomes hard even with like beefy machine that people have these days. And then the modeling, the problem is that usually at least, the problem is that your A100 GPU has 80 gigs of RAM range, that matter, and that can only fit, let's say, this can only fit a couple of million nodes with these embeddings. So in this particular case, I'm not sure if this calculation is actually correct. I think this should be like approximately for 600 million nodes. So I think the factor of 4 is somewhere missing. Okay. So sorry, my confusion was that you can fit the embedding table on the GPU. It's just that you need to fit two embedding tables and the backward gradients for them. That's why there is 4x factor that I was calculating when I made this table, but now I forgot about this. So, okay, so for graph representation, graph mining team at Google really loves distributed computation thingy. Google invented MapReduce 20 years back almost. It works well, thanks Ph.D. There are a couple of different approaches that other people take: graph compression and graph partitioning for very large scale graph mining. We don't love graph compression because, if you have a factor X for graph compression, let's say you can compress a graph 10x, then the moment a person comes with 11x graph to you, you can avoid it. And that happens more often than you can imagine. So whatever your graph compression algorithm, the person comes with an even larger graph, and then you can, it's just hard. Partitioning is just very hard to get right. There are very different types of graphs, and it takes like a graph partitioning expert to actually do something, and then you have to, every single person in our team should have been like a graph partitioning person, which was just possible, right? And then graph partition is also very particular. So we have random walk sampling as our target. So it's actually very simple to do MapReduce style job for random sampling, you have nobody leads to their neighbors, and then you just have a join, distributed join with a distributed hash table that's fairly cheap, easy, and then you have like kind of samples of their adjacencies. Skip that. Yeah, the algorithm is very, very simple. And then what we get in the end is kind of this like kind of histogram with different length that we travel from each and every node and to each and every neighbor. And then we can plug this histogram back in an objective function and optimize that if we knew how to optimize that. So the accelerating training is done with tensor processing units, which are full and are available, both in Google Cloud and academia. Google Cloud gives insane amounts of money for people to use their TPUs basically for free. For academics, they can apply for grants, win them, do production, that will be very happy. What is different between like a GPU and a TPU is that TPUs are organized in this amazingly, like I just want the amazingly looking racks of a couple of thousands of chips per pod, and they have a very like each particular TPU is kind of like smaller than a GPU, but they have a high amount of high bandwidth memory per chip. So, and that memory we can use. Let me just have a number in here in particular for like the latest generation. A pod has approximately it's like let's multiply 9,000 chips, and then each chip has like around 100 gig RAM. So you can combine them all together with super fast like bandwidth, and if you pay some money to Google, you will have a supercomputer with like 200 terabytes of RAM with very fast communication. That's just insane. We can shop so many graphs. So that's what we kind of did. We, even a smaller like subset of the pod has insane amounts of RAM. So we can like optimize crazy large embedding tables, relatively cheap piece of hardware. When compared across different architectures, we compared with the eFIS GPU machine. You can get 16 and 800s at a time, so no 800s are available, but they have exactly the same amount of RAM. And the computing system was Meta's Biography. It produces suboptimal quality embeddings at decently high speed. There is an academic system, Light-NE, that is a CPU-based system based on graph compression, so you cannot do really large graphs in there. The problem is that it produces very low quality results, which is great for speed, but not great for the actual production. So we actually have to, to serve Google customers and make everyone happy, we have to have good performance, like good quality in whatever we do. And this is a primary concern. Speed is like slightly secondary. Instant embedding is one of my older papers that does kind of CPU embedding at slightly slower scale, again on CPUs. And then huge CPU is kind of like our old baseline CPU-based system that is based on feeding a large amounts of CPU workers and have them communicate between each other in kind of a round-robin fashion. For gradient updates, it's super slow. It uses 5,000 CPUs, but it achieves good quality. The TPU system, though, only uses 64 accelerators, and then it produces high-quality results. I think I have a picture. Yeah, I get that the classic T-SNE picture to prove a point. We are very. Sorry,
what's the interconnection point? Big fan?
Yeah, so it's a proprietary system based on a very cool technology. It's optical instead of classical InfiniBand style connectors. You can find it in the paper description. I think it was introduced in the 4th iteration and has like some safety memory speeds. So I'll come to the latest part of my talk. This short block for TF GNN, our graph machine learning library TensorFlow. So just kind of a recap, we like to think about graphical networks as message passing operators, and then each node has kind of a state or embedding, and then we pass these embeddings across the edges. We have a tiny neural network to transform the state into a message. Then messages are updated and aggregated into something, a new state for multiple steps. And then final node states are read out, and then you do your node classification and prediction, clustering, whatever else on your final states. The cool things about NTNNs is that they really alleviate some complexities about handling multiple different node and edge types. That means we can model like this very complex systems I've been showing you, like videos, advertisers, users passing messages to each other, different kind of tiny neural network processors, and then you can easily model very different sets of features and so on. They can do different tasks, node classification, link prediction, graph classification, and like contrasted with the style unsupervised learning very, very easily. And like one of the plugs that TFGNN was used for this nice science paper for weather forecasting, and that's exactly like I would like to see this used on a very large scale as well. The same kind of style of thinking applies. You have a state, and then we try to predict the next state, and that's basically your weather forecast. And the system was proved like much significantly better than classical physics simulation systems out there back at the time. The MPNNs can be scaled to very, very large graphs through subgraph sampling. We have a kind of a blog post about how to do that specifically, but in general, it's nothing different than what I showed you with default style pipelines with random walk sampling. It's not that hard to transform. I mean, it's hard, it's engineering hard, but conceptually, it's not super hard to transform this random walk pipeline into the scalable sampling pipeline for very heterogeneous graphs. And that's the approach we again take to achieve scalability on very, very like large size graphs without kind of like limiting ourselves to the partition. Again, partitioning is just again hard when you have very complex graphs because you kind of don't know how to partition across different node edge types. So we're very happy to release TensorFlow GNN 1.0. I didn't realize this is like a we're 29th of February. We technically released TFGNN like in February. So it was this month that we released the first stable version. So now we are promising to support you basically forever for graph neural networks. There is this TensorFlow blog post about this. We're very excited to polish and solidify the library for like production use cases. And we kind of cover like different architectural layers. So this is serious software engineering. There is this data layer, data exchange, modeling, and kind of orchestrator layers for reasonably low-code solutions to graph networks. And then we handle like a bunch of nasty things that happen between graphs and machine learning accelerators such as TPUs. But first, again, one thing that is pretty useful in industrial settings is some kind of explainability. If we classify a node, we probably want to know why we need to classify that. So we will build explainability for the first class citizen system. That's the fun part for me. TPUs are very annoying to program for because they only accept static shapes at every step of their execution. We handle that for you if you use TFGNN. And we have like kind of a fun, tiny machine learning based optimizer for when you have a graph, you sample a graph, you shove these graphs into an accelerator, so we back them optimally, and then with minimal padding into a single batch of examples. and learn the optimal padding on the fly from actual data, which I think is very fun. This allows us to train like super fast on TPUs, and yeah, we have like in-depth call-outs to how easy it is, but it's surprising to see I was able to use that. Yeah, so take-home messages. We can model very hard systems with graph networks and graphs. Embeddings are fun, and we can scale to very large graphs, and with GNN, we try to make your lives more advanced now, very hard graphs for us. Thank you for attention. This is me. You can always reach me. These are links to the papers that I covered or talked about in this talk, and more good stuff that we will do this time. So we'll do for us. Thank you.
Thanks, everyone. So if you guys have any questions, we should have maybe 1 or 2 questions right now before the final.
What kind of approaches were the best on the TPU graph contest?
On the CPU graph contest, it was like a bunch of graph-based feature engineering that we didn't think about. I think that gave like a 40% boost from what we initially developed, which is kind of a nice lesson, right, for these things. Like on Quora, everything is pre-processed for you, and you're supposed to only use the features that you're given. In real life, you engineer some crazy feature from your data that actually gives you good performance, and that's what you're supposed to do. In terms of architectures, it was graph transformers, surprise. Once again, the graphs are large though, so it was a bit hard to adapt graph transformers directly, which is one fun part of the competition. So we hope actually to, involve, community more of this data sets about how to scale graph transformers to large graphs.
I'm still interested in that interaction. Maybe that would on please, and how can you compare with the community?
And the link. I don't have numbers on top of my head. I'm not a hardware guy. Last I checked, it was like 4 or 5x faster. Just on top of my head.
4 or
5x throughput. Yeah. Yeah. So. And you can only connect 16 cars with it. So you have kind of an upper bound in terms of like the amount of RAM your model can consume. Here we connected, let's say, like you can select a configurable slice of a TPU bot system. I think the last architecture is like 3D torus connected basically. And connect like arbitrarily many chips basically. So for this graph embedding experience, we connected 64 with superfast, and this is basically. So I guess in the interest of time, we'll.
Thank you.
Yeah. So do we want to use
Yeah, I should have one.